Right. So if I remember correctly, today we were going to talk about instantaneous and average power, and then also, excuse me, maximum average power transfer. So the instantaneous and average power portion should largely be a review of what you guys learned in your Circuits 1 class, so I'm not going to spend a ton of time on that. That being said, if there's anything that doesn't make sense or seems confusing, by all means, please ask questions and all of that kind of good stuff. Um, so let's consider a sinusoidally excited network, like so. So I'm just going to have some sort of sinusoidal excitation. Doesn't particularly matter if this is a current source or a voltage source, so I'm intentionally leaving it ambiguous. And I am sinusoidally exciting some linear network. It doesn't particularly matter what's inside this linear network. It's just important that it is indeed a linear system. So let's just call this a black box linear network. Excuse me. So we could use an oscilloscope or something like that to measure the voltage drop across the terminals of the network as a function of time. And we could use something like a Hall effect sensor or a current transformer to measure the current flowing into the terminals of this network as a function of time and see it as a, a time varying function. And so let's say that in general, the voltage drop across the terminals of our network could be expressed of the form Vm cosine omega t plus some phase angle theta v volts. And similarly, our current I of t could be expressed of the form Im cosine omega t plus some phase angle theta I, like so. So the power that is absorbed by our network is our instantaneous power. And our instantaneous power should be a function of time so that we can plug in any particular value of time and have an understanding of what the power is at that particular instant, right? So we should know by this point that power is simply the product of voltage and current. So I'm going to have simply V of t multiplied by I of t. And if I substitute in my generic forms for my voltage and current, I would have something like this. Vm cosine omega t plus theta v multiplied by Im cosine omega t plus theta I. Now I can simplify or reduce this down by applying a trig identity. So the trig identity that I'm going to use, I'm going to put it over here in blue, is that the cosine of some angle 1 times the cosine of some angle 2 is equal to 1/2 of the cosine of angle 1 minus angle 2 plus 1/2 the cosine of angle 1 plus angle 2, where in this case, omega t plus theta v is my angle 1, and omega t plus theta I is my angle 2. So applying that trig identity, I'm going to wind up getting 1/2 Vm Im cosine theta v minus theta I plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I as my instantaneous power. So we really have two distinct parts in this expression, okay? So I'm going to start with this right-hand part over here, okay? So what's interesting about this particular part is we have a sinusoidally varying component of our instantaneous power, which shouldn't really be surprising because, we've got a sinusoidal voltage and a sinusoidal current happening. But what's interesting is that the sinusoidally varying part of our instantaneous power is actually oscillating at twice the angular frequency of our current or voltage, okay? So our power is going to fluctuate twice as quickly as the input voltage or input current into our system, okay? So this is a twice omega AC power. And then over here on the left, we have essentially a bunch of constants, right? Because the magnitude of our voltage is going to be a constant. The magnitude of our current is going to be a constant. The phase angles for our voltage are constant. The phase angle of our current is a constant. And so the cosine of the difference of those two phase angles is in itself a constant. So we have what is essentially a DC term here. So if we were to plot this instantaneous power as a function of time, it might look something like this. So here's P of t measured in watts. Here's t measured in seconds. And I'll use blue for the hell of it. So we may see something akin to this. Where the halfway point between these peaks, which would be somewhere in the ballpark of right here, represents that DC portion of our instantaneous power signal. So since exactly half of the time our instantaneous power is above that dashed line representing the DC portion, and exactly half of the time it is below that dashed line, again representing that DC portion, that DC portion is really just simply our average power for our system. And then this guy up here obviously represents the maximum average power for our given system. And this part down here is then our minimum absorbed average power. Now, there's another interesting thing that's going on here. So what does it mean that in this particular region, the value of my instantaneous power is negative?
Power in that region that's actually taking power?
So I don't like the no power, and I'm not sure what you mean by taking power, but I think you're close, right? So based on the orientation of, the current is flowing into the positive polarity terminal here, we have been calculating absorbed power. So if we have a power that is lying below the horizontal axis, that means that we have negative absorbed power, which is the same thing as supplied power. So essentially, for brief periods of time, and it depends on how many energy storage elements we have in our system, what their values are, and all of that kind of stuff. But for brief periods of time, our load in this case is actually going to wind up supplying power or sending power back towards our source, okay? So we are going to see that this happens anytime we have any type of energy storage element in our system, okay? So let's mathematically describe how that works, okay? So let's look at what would happen if our load was just purely resistive, okay? So for some resistor R, we know that the magnitude of our voltage is just equal to the magnitude of our current times the resistor value. And we also know that the phase angle of our voltage and the phase angle of our current are the same things. These are some of the relationships that we introduced when we were talking about our frequency domain relationships between current and voltage for capacitors, inductors, and resistors, okay? So that's where these expressions came from. So I can algebraically manipulate this essential Ohm's law expression right here. And I can express the instantaneous power absorbed by a resistor purely in terms of voltage-related quantities or purely in terms of current-related quantities. So I could say that the instantaneous power absorbed by a resistor would actually wind up being 1/2 the magnitude of my voltage squared divided by R times a factor of 1 plus cosine of twice omega t plus twice theta v, okay? Where I'm doing nothing but substituting in those relationships into this expression that I have up here. And we can infer from this then that the DC portion of this instantaneous power is the average power absorbed by a resistor. So in this case, that would simply be 1/2, Vm squared over R. Finding my instantaneous power in terms of current is going to give me the relationship 1/2 Im squared times R times 1 plus cosine twice omega t plus twice theta I. And we can see from this relationship that our average power absorbed by our resistor is 1/2 Im squared times R. So graphically, if we had a purely resistive load, we would have a situation like this. So here's PR of t. Here's t. And what we would see is that our instantaneous power should touch the horizontal axis, but it should never actually cross it, okay? So our maximum power up here is literally just going to be twice our average power. And our minimum power is simply going to be 0. So this occurs because a resistor is literally incapable of storing electrical energy. All it can ever do is convert electrical energy into heat, okay? So we are going to have, for a purely resistive load, it's going to contribute only absorbed power that is oscillating between some maximum value and 0. And that maximum value, like I said, will always be exactly twice the average power, okay? Now, if we looked at an inductor, we know that the magnitude of the voltage drop across the inductor is going to be omega L, our reactance, multiplied by our magnitude of our current. And we should also know that the phase angle of our voltage should just be the phase angle of our current plus 90 degrees. Okay. And again, these relationships came from a previous lecture. So if I plug in these relationships and algebraically manipulate them, what I'll wind up seeing is that the instantaneous power absorbed by an inductor is going to come out to be 1/2 times the magnitude of the voltage squared divided by what is essentially the magnitude of the impedance, omega L, and then I'm going to have cosine twice omega t plus twice theta v minus 90 degrees, where everything is in terms of voltage, and in terms of our current, we would have 1/2 Im squared times omega L cosine twice omega t plus twice theta I plus 90 degrees. So what is the DC part of this power? Nope. That's the magnitude. So that's the magnitude of the power, but it's being multiplied by cosine twice omega t. So that's definitely sinusoidally oscillating. Sorry, what? I'm sorry, I'm half deaf. 20i? That's twice theta I, but no. So there is no DC part. It's literally zero, right? So let's talk about why it's zero pretty quickly, but it should be fairly easy to figure out. We know that theta v is equal to theta I plus 90 degrees. So that means that our phase angles for our voltage and current are 90 degrees out of phase. So if I have theta v is equal to theta I plus 90, then theta v, sorry, minus theta I is literally going to be theta I plus 90 degrees minus theta I. Those guys cancel each other out. And I'm taking the cosine of 90 degrees in that DC part. Well, the cosine of 90 degrees is literally zero. So if I were to plot what's happening as a function of time, like I've done with the others, we would see something akin to this, right? So here's our instantaneous power for our inductor as a function of time, where time is measured in seconds and power is once again measured in watts. And we would see some sort of wave shape that looks like this, where exactly half of the time our inductor is absorbing power and exactly half the time our inductor is supplying power back towards our source, right? We'll find out here in a moment or two that the capacitors are going to do the exact same thing. So our energy storage elements are always taking in energy and then sending them straight back towards our source. When we talk about complex power and stuff like that next Monday, we'll see how that impacts quantities like power factor and things like that. So we can see here very easily that the presence of any inductance in our system is going to be where some of this effective sending energy back towards our source is coming from, okay? So when we have capacitors, we have a very similar relationship for our magnitudes as well as our phase angles, except that current and voltage are going to switch places, right? So we would have Im is equal to omega c times Vm, and then we would have theta I is equal to theta V plus 90 degrees, okay? And so if we substitute and manipulate these relationships, we wind up getting an instantaneous power absorbed by our capacitor is going to be 1/2 times our magnitude of our voltage squared times omega c, and that's multiplied by twice omega t plus, twice theta v plus 90 degrees, where everything is expressed in terms of our voltage, and in terms of our current, that's going to look like 1/2 Im squared divided by omega c cosine twice omega t plus twice theta I. That should be minus 90 degrees. And from here, our average power absorbed by a capacitor is also 0 because there's no DC portion for this instantaneous power. I'm not going to bother graphing the plot for PC as a function of time because it's essentially going to be exactly the same thing as PL, just shifted by 90 degrees. Okay. So let's see here. I'm trying to decide if I want to do a formal derivation for average power, but I don't think I'm going to bother doing that because we did it back in circuits 1. And if I need to do it, we can do it in our next class meeting when we talk about effective values and all of that kind of good stuff. Okay. So we've covered instantaneous power generically, right? So let me just make a couple of quick annotations here. So this expression is the most generic representation that we have, okay? It works for everything, okay? It requires us to know both the voltage drop across our network of interest as well as the current flowing through our network of interest, okay? So I want to be very clear here because this is a place where I see particularly a lot of circuits 1 students get confused. And if we need to work a numerical example, we can definitely kill some time and do that. But our circuit analysis is still going to be occurring in the frequency domain, even though this is a time domain relationship, right? So we would simply, in order to apply this equation, we would analyze our circuit in the frequency domain, exactly how we've been doing things. And then we would just take the constituent parts of those phasors that we need to plug them into this equation, right? So this magnitude of the voltage Vm, so let me just spell this out explicitly here, right? So Vm is literally just the magnitude of some phasor voltage V. And Im is obviously then just the magnitude of some phasor current I. Well, theta V is literally just the angle of some phasor voltage V, and theta I is just the angle of some phasor current I. So we're literally just taking those parts out of our frequency domain analysis and then simply plugging them in to any of these particular equations. So we're still not doing any actual circuit analysis in the time domain because it's horrifyingly gross and involves way too much trig and calculus, and nobody has time for that. Okay. Another thing that I want to point out to you guys is that our angle here, so twice omega t is an angle that is expressed in radians. Typically speaking, our phase angles are expressed in degrees. So you're going to have to make a choice as to whether you want to convert this part into degrees or this part into radians to put anything like that actually in your calculator. Because your calculator is just going to use whatever setting it's on and just assume all of the angles are of that form, right? So we've used that conversion factor a couple of different times, back when we were talking about analyzing our underdamped circuits when we were doing our transient analysis to put stuff into LT spice, right? The conversion factor is simply 180 degrees is the same as pi radians, and just use that as is appropriate in order to make sure that your numbers come out right. So those are the most common mistakes that I see students make when trying to apply any of these equations, is they somehow wind up getting complex numbers inside of these time domain functions, which is inherently wrong. Complex numbers are only frequency domain things. So you should literally just get normal numbers and then sinusoidally oscillating kind of thing. And then messing up the quote unquote units on the angles can also cause you to get, you know, everything else right and just have the phase angle of the resultant be very wrong for my answers. So just wanted to nip those kind of questions in the bud. All right, so before we move on from here and talk about maximum average power transfer, does anybody have any questions, comments, or concerns? Okay, like I said, this part should have been overwhelmingly reviewed. So before we jump into this new topic, I want to tie things back to how we approach this with DC circuits back in Engineering 221, because some of these relationships are going to crop up again, okay? So back in 221, we essentially found that if I have a circuit that can be represented by a Thevenin voltage source in series with some Thevenin resistance, and then connected to this Thevenin equivalent circuit is some generic load resistance, which I'm just going to call right here RL. We found that the maximum power that could be supplied by our Thevenin equivalent circuit was 1/4 times the Thevenin voltage squared divided by the Thevenin resistance, under the constraint that our load resistance had to be equal to our Thevenin resistance. Does anybody remember this vaguely? Or more than vaguely, hopefully, but yeah. Okay. So this result was determined by maximizing a particular function, okay? So if I say that this is the voltage drop across my load resistor VL, and this is the current flowing through my load resistor IL, then the power absorbed by my load is just going to be the product of VL and IL. And so if I'm remembering correctly, that's going to come out looking like VTH squared times RL over RTH plus RL quantity squared. That looks right from Ohm's law and voltage division and multiplying those things together, right? So we came up with these relationships essentially by taking the derivative of this guy and figuring out what value of RL makes that power hit its maximum value. And we found that that was when RL is equal to the Thevenin resistance, okay? Well, we're going to do something similar here, but now we're going to do it in the frequency domain. So instead of dealing with resistances, we're going to have to deal with impedances. And instead of dealing with some Thevenin DC voltage, we're now going to be dealing with some phasor Thevenin voltage. Okay? So for AC circuits, we might have something that looks like this. Okay? So let's say that this is now some phasor Thevenin voltage. This is now my Thevenin impedance, ZTH, and I'm going to connect to this electrically equivalent representation of a circuit some load impedance, ZL. Okay. Well, we know that the average power absorbed by my load impedance ZL should be, in the most generic form possible, 1/2 times the magnitude of VL times the magnitude of IL cosine the angle of theta VL minus theta IL, where this is literally just 1/2 VM IM cosine theta V minus theta I, like we just came up with 20 minutes ago for our generic system, okay? I'm just working explicitly with these phasor quantities now, okay? So that is our average value for our power for this generic load. And we need to figure out essentially what are the conditions that are going to be required in order to maximize this particular average power. And unfortunately, it is a bit more difficult than what we did with just simple DC circuits, but it's not anything hugely difficult by any stretch of the imagination, okay? So essentially what I want to do is I want to just pick this thing apart, okay? And then we're going to plug our constituent parts into this generic equation for average power and kind of see what shakes out, as opposed to doing too much calculus with this, just because the calculus with complex numbers gets real gross real fast, okay? So let's start with finding the magnitude of VL, something like that, okay? So I can say that my phasor voltage VL is just going to be, using voltage division, my Thevenin voltage multiplied by ZL divided by ZTH plus ZL. Does anybody have any problems with that application of voltage division? So what I could do now, and this will actually make finding the magnitude of this a little bit easier here in a moment, is I'm going to split this thing up, or I'm going to express those impedances in rectangular form, okay? So this would look like my Thevenin voltage multiplied by the real part of my load impedance, RL, plus J times the imaginary part of my load impedance, which is going to be just the reactance, XL. And then down here, I'm just going to split my Thevenin impedance up into its real part, RTH, and its imaginary part, XTH. And my load impedance back into RL plus JXL again. And now, as one last little manipulative step here, in my denominator, I'm going to choose to add my real parts together and add my imaginary parts together, which would give me the relationship VTH times RL plus JXL divided by RTH plus RL plus J XTH plus XL, like so. So the magnitude of this voltage, VL, would then simply be the magnitude of this expression here. And the reason why I've broken it up like this is because it's going to be really easy to find the magnitude in this form. So the magnitude of our Thevenin voltage is literally just the magnitude of our Thevenin voltage. Well, the magnitude of RL plus JXL is going to be RL squared plus XL squared. And then I take the square root of that whole thing, right? That's literally just Pythagorean theorem. A squared plus B squared is equal to C squared. So C is equal to the square root of A squared plus B squared kind of thing. And I can do the exact same thing for what's going on in my denominator, right? So I will have down here, RL plus, excuse me, RTH plus RL. Let me do it the same way. Squared plus XTH plus XL squared. Close that guy off and then do to the 1/2 power to take the square root of that whole denominator. And so in a very similar treatment, I'm going to now find what my load current is and what the magnitude of that load current is, right? So using simply Ohm's law, I could say that IL is just going to be VTH over ZTH plus ZL. And jumping over that intermediate step, since it's effectively the exact same thing that we just did, this is going to come out looking like VTH over RTH plus RL plus J XTH plus XL. And from here, the magnitude of my current is then just going to be the magnitude of my Thevenin voltage, phasor, over that exact same denominator that we saw for our voltage. So here we'd have RTH plus RL quantity squared plus XTH plus XL quantity squared, that whole thing to the 1/2 power. Okay. So just to recap what our process is, we have determined the magnitude of VL so that we could substitute it into this guy, no problem. We have found the magnitude of IL so that we can throw that in as a substitution, no problem. So the last thing that we need to figure out is cosine theta V minus cosine theta I. And this is probably the harder part to wrap your head around, but it's not going to be too particularly crazy. So if I were to make a plot on the complex plane of a generic impedance ZL. So here is my imaginary axis. And let me draw this better. Here is my real axis. Let's say that this vector right here represents my load impedance, okay? Well, the projection of this load impedance onto the real axis is just RL. And the projection of this impedance onto the imaginary axis is just XL, right? This angle right here is theta VL minus theta IL, because, just to remind you all, ZL is going to be the ratio of phasor voltage VL to phasor current IL, which would be the magnitude of VL with an angle of theta VL over the magnitude of IL with an angle of theta IL is just the magnitude of my impedance with an angle of theta VL minus theta IL, like so. So I can use this graphical representation to actually figure out what cosine of theta VL minus theta IL is going to be, because I'm remembering my high school trig class correctly. Cosine is simply the adjacent over the hypotenuse, right? So the adjacent in this case, so let's write this out down here. So cosine of theta VL minus theta IL, the adjacent bit here is literally just the real part of my impedance. And then my hypotenuse is just essentially the magnitude of my impedance, which I'm going to choose to write as RL squared plus XL squared to the 1/2 power. So just the square root of the real part squared plus the imaginary part squared. Again, nothing more than good old Pythagorean theorem applied to an impedance in this case. So now I know what cosine theta VL minus theta IL looks like. And so I can literally just plug that stuff in. So if we come down here, we could say that our average power absorbed by our load impedance ZL is going to be 1/2 times. Now I'm going to simply substitute in the magnitude of my Thevenin voltage. There's going to be the magnitude of my load voltage. So that would be the magnitude of VTH times RL plus XL. Excuse me, both of those should have been squared to the 1/2 power over RTH plus RL squared plus XTH plus XL squared, all of that to the 1/2 power. So that's my magnitude of my voltage. Now I'm going to put in the magnitude of my current, just direct substitution here. That's the magnitude of my Thevenin voltage over that exact same denominator. Close that off. And then lastly, I need to have my cosine of theta V minus theta I, which I found to be RL divided by RL squared plus XL squared to the 1/2 power. And now I'm going to simplify this thing a bit. Okay. So hopefully we can all see that I have a common factor of the square root of RL squared plus XL squared here in the numerator of my voltage term and the denominator of my cosine term. So those guys are going to cancel each other out. Since my denominators for the voltage term and the current term are exactly the same and they both have a square root, when I multiply them together, that's just going to get rid of that square root sign. And so the result of this is going to simply be 1/2 times, let me put my denominator down here first, RTH plus RL quantity squared plus XTH plus XL quantity squared. And then in my numerator, I'm simply going to have the magnitude of my Thevenin voltage squared times the real part of my load impedance. Okay. So we've done a whole lot of setup work here, but now we actually have things in a form where we can look at it and start making some inferences as to what's going to happen here. Okay. So, and I know this is going to be an oddly framed question, but I don't know of a better way to ask it. What do our reactances do to our average power here? Let me just make this real clear that this whole thing is the average power absorbed by our load impedance.
We don't do anything because they're all.
Do you see a single J in here? It makes it smaller. So the presence of any reactance is going to make my average power smaller. So if I want to have maximum average power transfer, I need that reactance term to go to 0, okay? So this is the first thing that we can observe. In order for maximum average power transfer to occur, our load reactance XL must be negative our Thevenin reactance. Okay. So that when XL is equal to negative XTH, that reactance term goes to 0, which forces my average power term to have a smaller denominator and thus be a larger value than it could ever be with any reactance in the system to begin with. Are we okay with that? This makes logical sense. So what does this reduce to under that constraint? Well, let's look at it really quickly, right? So the average power absorbed by our load impedance when we're forcing XL to be equal to negative XTH simply comes down to then a factor of 1/2 times the magnitude of our Thevenin voltage squared times our load resistance divided by our Thevenin resistance squared plus our load resistance squared. No, that's wrong. Sorry. That's where the squared should go. My apologies. So how do we maximize this thing? So we have a simple expression now where we're only dealing with like real numbers, right? So if we wanted to maximize this function, we could approach it exactly like we did in circuits 1. We could take the derivative of this expression with respect to RL and then set that equal to 0 to find the maximum value and then plug that value of RL back in. But I want you to look at this guy right here and then look at what we maximized to get the constraints in our DC circuit. It's literally the exact same thing, except that there's a factor of 1/2. Because this value of VTH right here was just a magnitude of that voltage, right? So we have effectively already done that part back in circuits 1. So the other condition for maximum average power to transfer to occur is that RL has to be equal to RTH. So when we put these two constraints together, we find that maximum average power transfer occurs when our load impedance ZL is equal to RTH minus JXTH, which is the exact same thing as the complex conjugate of our Thevenin impedance. So that forces the resistances to be the same while canceling out the reactances that lower our average power. Okay. So with this in mind, then we could figure out what our average power relationship is actually going to be. And what we would see is that the maximum power that can be absorbed by our load resistance ZL, and this occurs again when it is equal to ZTH conjugate, is going to wind up being 1/8 of the magnitude of our Thevenin voltage squared divided by RTH in the event that we have our circuit expressed as a frequency domain Thevenin equivalent circuit, or it would be 1/8 of the magnitude of our Norton current squared times RTH if we have our circuit expressed as a Norton equivalent circuit in the frequency domain. For what it's worth, that factor of 1/8 is literally just this extra factor of 1/2 multiplied by the 1/4 that we had from the DC analysis.